Thank you very much, Anthony, and I.M. for inviting me to this occasion, the Exopolitics convention of yours. I can't think of anything that is more relevant to exopolitics than the discovery of extraterrestrial life. So that's what I'm going to talk about for the next hour or so, the latest trends, you might say, about the existence and the discovery and the acceptance of extraterrestrial life. So it's connected with sociology and politics ultimately, but let's first start with the science. This is an image, a very stunning picture of comet Hale-Bopp, which appeared in our skies in 1997. It's a fantastic image. And images of this kind, similar sights, would have greeted our prehistoric ancestors from time immemorial, from tens of thousands, hundreds of thousands of years ago. And then, in those days, our Milky Way, the band of light that you see across the night sky, which is comprised of hundreds of billions of stars, this Milky Way would have been showing 100 times perhaps more stars than we can see today with our naked eyes under our heavily polluted skies. Even if you go into the North Country here, you've got to really struggle very hard to find a location where you can have a clear view of the night sky. And such views, such images of the night sky would, of course, have been the norm in our prehistoric ancestry. And the question that must have been asked from time immemorial must surely have been, where do we humans on this tiny, insignificant planet fit into such a grand scheme of things? Because the image picture that you see here is really a stunning image of millions, billions of stars, little points of light that essentially direct us to the heavens, almost direct us to the heavens for our origins. So the question that would have been asked, I think, time and time again, throughout our ancient ancestry and our history would be this question: how did life begin? Coming back to more recent times, leaving prehistory aside, to ancient philosophers, the origin of life was one of the easier problems that they had to grope with. For the philosopher Aristotle, for instance, life arose spontaneously from inanimate material of the earth. For instance, he argued, or he stated, that a mixture of warm earth and morning dew could lead to life, and life in the form of fireflies twinkling like stars in the night sky. So this was the kind of image and picture that was depicted by our ancient philosophers in the days of classical Greece. And there were many variants on the warm earth and morning dew, but by and large, the message was the same. If you mix inorganic material, the material of the earth and water and so on, in certain ways, you would get life. Today, modern science comprehends full well how fireflies light up. They use a chemical called luciferase, an enzyme that essentially fluoresces and produces these brilliant sights of fireflies twinkling like stars in the night sky. But the origin of life remains perhaps the hardest unsolved problem in the whole of science. Very few current practitioners in this area of origins admit that it's an unsolved problem, but I think if you're really honest, you have to admit that no one has solved the problem of how life began from non-life. What I would like to do today is to argue that the transformation, the conversion of non-living chemicals, non-living material, to living material could not have happened on this tiny, tiny, insignificant planet of ours, the Earth. And so it seems logical that our attention must be turned to bigger things, to cosmic settings. We could perhaps think of the 100 billion comets that surround the entire solar system, the planetary system. And in these 100 billion comets, the total amount of organic chemicals that are present exceeds the mass of the whole Earth. So it's a huge gain in terms of organic chemistry, organic chemicals that you have if you go from the Earth to the 100 billion or so comets. But even that may not be enough to make the transition from non-life to life. So let's go then think of moving further into the whole Milky Way galaxy, the Milky Way galaxy that I showed you in the early images. And there are 100 billion stars that are like the sun, and presumably around each of these stars there would be a cloud of 100 billion comets. So you have a huge gain if you go to the totality of stars like the sun encompassing the whole Milky Way system, our galaxy. Then, if the galaxy itself is not big enough to make this important transition from non-life to life, the next system that you have in astronomy is a local group of galaxies, a group of galaxies that each one of which looks like the Milky Way system, looks like our own galaxy. Each one of these consists of 100 billion suns. And then, if that's not big enough, go to the local supercluster. So you go higher and higher in the hierarchy of things, and ultimately to the whole universe, to seek an answer to the most important question in the whole universe, in fact, in the whole of science: how did life begin? The trend, I think I would try to argue, would be to favor a one-off cosmological origin of life. An origin of life that is extremely unlikely, but happened because we know it happened, because certainly because we are here, it happened somewhere. And the best setting for this improbable, highly improbable event, and I'll talk a little bit about the probabilities in due course, but if you're going to make this improbable transition happen, then it is wise to go to the biggest available setting, and the biggest available setting must embrace the whole universe. Once life starts, however, then I would argue that the transference of life, the moving of life from one place to another by a mechanism that's called panspermia, using comets as the vehicle of transport, this is relatively easy, and this is, I would argue, is the preferred mechanism by which life originated, the most likely mechanism by which life originated and arrived here on the Earth. The concept of panspermia itself has very ancient roots. It goes back, in fact, in Western traditions, it goes back to classical Greece. The philosopher Anaxagoras, who lived from 500 to 428 BC, proposed that living seeds, or what's called spermata, were distributed widely throughout the universe. So life seeds, he argued, were everywhere in the universe, in the cosmos. But not everything that is wise and wonderful started in the Western world. Even much earlier, in the Vedic traditions of ancient India, around 2500 BC, the idea of life being a truly cosmic attribute was widely prevalent. The ideas that relate to the sort of modern panspermia, that if you look at the internet, panspermia is talked about in various degrees of belief or lack of belief. The originators of the modern ideas of panspermia were essentially started in the late 19th century with Svante Arrhenius, then with Fred Hoyle and myself in the 1970s. And it involves essentially a synthesis of astronomy and biology. And I should also, in passing, tell you that the whole science of astrobiology was essentially started by the work that Fred Hoyle and I did in the 1970s. The word astrobiology was actually proposed by Fred Hoyle in a lecture that he delivered in Cardiff in 1981. Not many of our American colleagues who have embraced astrobiology very late in the day acknowledged this, but we, in fact, invented even not only the science of astrobiology, but the term itself. 35 years ago, when we started talking about these things, any connection of life with comets or with the external universe was considered to be an outrageous heresy. And this whole series of books that you see there that we started writing in the 1970s, starting with Life Cloud and ending with one of the most recent books, Comets and the Origins of Life. At the beginning, this was regarded as a heresy. Had we lived in the Middle Ages, we would perhaps not have survived. We would have been burnt at the stake. Well, 35 years afterwards, the situation is beginning to change. Theories of panspermia are coming to the fore, and we may well be, I think, at the present time, at this very moment, at a tipping point for a major scientific revolution, which would have possibly the widest repercussions across the whole of science, across maybe the whole of sociology and humanity generally. Let me first just give you a brief outline of the logic that underlies panspermia. Panspermia follows from two facts that are very difficult, impossible to refute. The first of these facts was actually discovered by Louis Pasteur, who everybody in biology considers to be the father of biology, father of the science of experimental biology. Pasteur in 1870 showed through a remarkable series of experiments that microscopic life forms are always derived from other microscopic life forms. You cannot generate life spontaneously in the way that Aristotle suggested in the days of classical Greece. And the idea that Pasteur essentially cemented in the history of science was that panspermia essentially was what he showed to be the correct way to understand how microbes behave. He showed, for instance, that processes such as the fermentation of wine and the souring of milk did not occur if you prevented microbes from entering either the milk or the wine. So you needed microbes to start these processes. The second fact that supports panspermia and makes panspermia essentially inevitable is the ability of microorganisms to survive extreme conditions of space, extreme cold, extreme heat, extremes of radiation, ionizing radiation, cosmic radiation, desiccation. All these are conditions that microbes are known to withstand, and they have been researched extremely actively in the last 2 decades. In fact, the whole of modern astrobiology, I think, is essentially confined to the study of the extreme properties of microorganisms, and very little else is done in astrobiology outside of our own group that involves myself and my colleagues. So, but the important things that they do, I think, the other people in this area do are they're certainly related to panspermia and supports panspermia very strongly because they show that microorganisms are essentially space travelers. They are born space travelers. Two recent discoveries, I believe, confirm that bacteria are indeed born space travelers. One is the discovery within this fossilized bee that is trapped in amber. It's been trapped in amber for 30 million years. And if you look at amber, if you wear amber around your neck or something, if you look very hard with a magnifying glass, you can see insects very often in the amber. And scientists recently have dissected the insects in the amber, deep in the amber, and found that they contain, in the guts of these insects, there are microbes that have remained viable for 30 million years. Even more remarkable, in these salt crystals that were discovered in a salt mine in New Mexico, it's been found that viable bacterial spores have lain dormant for a full 250 million years. So these have been trapped in amber for 250 million years, and they can be cultivated, grown when you give them suitable nutrients. Well, the importance of both these discoveries, the bacteria in the amber and the bacteria in the salt crystal, is that the Earth, everywhere, if you look at the ground here, you think that you're in perfect freedom from radioactivity. You're not. There's always a natural radioactivity, background of radioactivity, averaging something like 1 rad per year. And the natural background radioactivity that would affect these bees and the insects, the bacteria in the salt crystals, gives huge doses of radiation, of ionizing radiation, 30 million rads in the case of the bee, and 250 million rads in the case of the insect, of the bacteria in the salt crystals. On this evidence alone, I think one could easily maintain that life is transported with impunity, complete impunity, from one planetary system, from one star system to another. And so the galaxy, on this basis, if you can transfer life so easily across these various stars, the different stars in our Milky Way system, our galaxy will be one connected biosphere, one gigantic connected biosphere. So forget about a biosphere that is constrained to the Earth. The biosphere at least extends, our biosphere extends across the whole galaxy. A little bit more about the Pasteur life from life logic, because that's what he discovered, that life is always derived, microscopic life is always derived from other microbial life. This logic, of course, operates for all types of life. It operates in the case of ourselves. We are derived from parents, from grandparents, and all the way down the line to our prehistoric ancestors. That same logic goes through the fossil record. Large animals are connected with the smaller animals and less complex animals, all the way back to what is called the Metazoan explosion, the great explosion of multicelled life that happened about 500 million years ago. 540 million years ago, there was a sudden explosion in multicelled life, in insects and so on. It all happened very suddenly. And then beyond that, older than that, we know that the oldest evidence for microscopic life on the Earth exists from 3.8 to about 4 billion years. And this evidence is in the form of the ancient rocks, the most ancient sedimentary rocks that were deposited at the time of intense comet and asteroid bombardment. So you have the oldest, very, very oldest evidence of microscopic life happening, just emerging on the Earth, appearing on the Earth at a time that we know the Earth was severely bombarded by comets. And this epoch of bombardment is called the Hadean epoch, the epoch of hell. So beyond that, going back to the Pasteur life from life logic, there are two possibilities. How did this first life that appeared on the Earth at 3.83 to 4 billion years arise? Did it arise from chemistry here on the Earth, chemical evolution, or did the same logic, life coming from life, persist before and continue before the Earth itself was formed, perhaps? Leading then to a cosmic origin of life, leading to panspermia. The chemical evolution idea option is essentially the old primordial soup theory that is the starting point of all textbooks. We are told that life started in a primordial soup. For far too long, there was no empirical basis for this, but this is what we've been taught in schools for close to a half a century. This is essentially a pre-Copernican idea, and I stress that it has no basis in logic and it is no basis in fact, and I shall argue further that it is fatally flawed. The primordial soup theory was proposed by Oparin, the Russian biochemist Oparin, and the English biologist Haldane in the 1930s and 1940s. And it gained a measure of credence after the classic experiments that were done. This flask here is a representation of the experiment that was done by Stanley Miller and Harold Urey in 1951. And they showed, in a very clever experimental setup, they showed that amino acids and other organic molecules needed for the origin of life may be produced in the laboratory. And this, at the time, was thought to be a great triumph because in the 1930s and 40s and so on, it was believed that organic molecules were essentially important components of life and could only be formed from life. So these guys then showed that some of these compounds could be formed inorganically, easily in the laboratory. But it's no good just getting the organic molecules, amino acids, nucleotides, sugars. That's useless. They are a far, far cry from life. It is the transition from organic molecules to what I would like to call the magnificent edifice of life that cannot happen easily. In fact, it can happen only with the remarkable improbabilities that I want to just discuss now briefly. It is the ordering of these molecules, amino acids, for instance, that are crucial for life. It's no good just getting the 20 amino acids made in the flask, the kind of flask that Urey and Miller had, but you need to string those amino acids into very, very special orders, arrangements, and that is the crucial part of a living system. For the simplest bacterium that we think we have knowledge of nowadays, it's called Mycoplasma genitalium. The probability of its crucial enzymes, it has about something like 450 enzymes. Each of these enzymes are made up of 20 amino acids, 20 distinct amino acids strung in a very particular orders, arrangements. And the probability of these 450 enzymes in Mycoplasma genitalium coming to be assembled in a primordial soup by random processes can be estimated in a very simple calculation that can be done by any A-level student of mathematics. And the probability turns out to be 1 in 10 raised to the 1,000, equivalent to 500 people. There's not 500 people here, but maybe running close to that. If I give each of you two six-faced die and ask you to throw it all at once, it's the same as the probability of 500 people throwing a double six. To overcome such a horrendous improbability, and you have to agree that this is not a probability that any betting person would take on lightly, it would surely pay handsomely to go to the biggest available system And the biggest available physical system in which life could originate is the entire cosmos, the universe itself. Cosmologists believe that the universe started with a Big Bang some 13.8 billion years ago. Within the last 2 months or 2 or 3 months, that has increased from 13.7, I think, to about 13.83 billion years ago. But some time like that. And that, I should point out, is not a great excess on the age of the Earth. The Earth itself is 4.5 billion years. So this is about 3 times the age of the Earth, the whole universe. How early could life arise in this Big Bang universe is a question that one could ask. Certainly not at the Big Bang itself. It is too hot. Not within minutes or hours after it, because again, there are problems. The material has not yet formed and so on. So it has to be not too early, not too hot, and the region that I marked with a big arrow there is a region where life could not have started because there were no elements, chemical elements would not have formed. There are many different models of this Big Bang universe, and in one particular model of the universe, the conditions for life emerging, I believe, are met at a very early stage in the history of the expansion. And this could happen between 300,000 and 1 million years after the Big Bang. I should also tell you that in the last 2 or 3 months, there have been many people who have argued that the oldest stars in our galaxy itself may be very close to a million years after the Big Bang. They go back in time very close to the Big Bang itself, within maybe 1 or 2 million years, which means that stars and planets and so on were already in place very close to the beginning of the universe. So in this particular model that I want to just talk about very briefly, 300,000 years after the Big Bang, the entire universe is a plasma. It's ionized gas, hydrogen, helium, ionized. The nuclei separate from the electrons. And at this moment in time, the positive ions, the positive parts of the atoms and the negative electrons recombine. They get together again, and that's called the recombination era. And in the process of recombination, the whole universe becomes unstable and just breaks up into eddies. And these eddies, little eddies, are on the scale of the mass of the Earth. So just imagine the whole universe breaking up into clumps of material, each of which has the mass of the Earth. And the little p there on the right is a schematic depiction of one of these planets, or primordial planets that formed within the first million years of the history of the universe. Now, at this time, the universe is very compact, and there are interactions taking place frequently between these different blobs of material. They collide, some of them coalesce and form massive stars that evolve very quickly. And the massive stars evolve, produce chemical elements. All the chemical elements of life are made on a very short time scale. They explode and scatter this material, scatter the life chemicals, life atoms, essentially to infect all of the other Earth-massed planets. So the whole universe then is essentially one primordial soup that is connected. Some 10 to the 80, 10 raised to the 80, 1 followed by 80 zeros of Earth-mass planets are separated by very short distances. And because the universe is compact at the time, the typical distance between the two of these is like the distance between the Earth and Jupiter, and that's no distance at all in cosmic terms. So they form a connected primordial soup. So life arises, and as I told you earlier, life had to arise because we are here. So let's seek the best possible scenario for life to arise in the universe inorganically. And that scenario, I think, is in the early universe where these conditions of liquid water and organics are present in a multitude of watery bodies. So life arises in one such body. The orange blob is the one where life arises, where all the improbabilities are overcome. And then it just spreads because of the closeness of one planet to another. And multiple links essentially is tantamount to some kind of Darwinian evolution. Within this huge set of primordial planets, if you once form a microorganism, if it originates, then the one becomes 2 in something like 4 hours, 2 becomes 4 in 8 hours, and so on. If you ask the question, how long would it take for the whole of this material to be converted into biological material, into living material, the answer is only 1 million years, okay, because of the exponential replication being so efficient. And life thereafter, once it started in the early universe, it spreads with the expansion of the universe. In this theory, the mysterious dark matter of the universe, and we've all heard of that for a very long time. We don't know what it is in terms of its material, but in this particular theory, it is in the form of frozen primordial planets or gigantic comets that harbor life, microbial life, that originated very close to the dawn of the universe itself. Is there evidence for such material, dark planets, frozen planets in the present day? And the answer is yes, there is a huge amount of astronomical data now that point to the presence of unseen planets everywhere in the halo of our galaxy. And so we argue that halos of galaxies like our own Milky Way contain the life-bearing frozen planets that essentially feed the disk of our galaxy where stars and planets form with life. According to this point of view, stars and galaxies form from the frozen primordial planets that are already endowed with the original legacy of cosmic life. Here in this picture, that blue blob that you see moving upwards towards a region of the formation of stars is a place where there is evidence of water and organic material that is essentially a degraded or disintegrated frozen primordial planet that is coming into the disk of the galaxy, falling in from the halo. What are the predictions of this kind of theory? The prediction would be that interstellar dust clouds from which stars, comets, and planets form are chock-a-block with material that is derived from microorganisms, from life itself. Is there such evidence? Is this prediction met? But first, how could this be tested? How could we really test for the presence of life chemicals in these star-forming clouds, in these dark clouds in space? How could we show that the detritus of living cells pervades these clouds? This is the Eagle's Nest Nebula, a very famous cloud of dust in the Orion Nebula, which is forming many, many stars at the present time. The way that we look at this or study this is to look at the light from a distant star. The star that is on the top left is a distant star. It crosses this dark cloud, and the light of the star that traverses the dark cloud leaves a signature of the material that it encounters, the material through which it traverses. And from studying the light that emerges from this star through the dust cloud, we can infer sizes, shapes, and compositions of the particles. All this can be done from the application of straightforward physics and mathematics. Evidence for the biogenicity of interstellar dust, derived in this manner that I describe now, has existed from 1978, and has steadily grown. This was one of the first determinations of the points, the astronomical observations of a source of light, infrared light, near the center of our galaxy. The curve that I've drawn there, that is drawn through those points, was a prediction of bacterial dust that could exist, that might exist in the interstellar dust clouds. The correspondence, the close agreement between the curve and the astronomical data points implies that something like 1 in 3 carbon atoms in interstellar dust in space is tied up in the form of a bacterial type material. And more of such data came as with the passage of time and over wider and wider wave bands. And this is a picture that shows the points in this picture this represents a dimming of starlight over a region from the far infrared to the far ultraviolet, and the curve is a prediction of a biological model of the dust. So it's a mixture of bacteria, degradation products of bacteria, including viruses and free aromatic molecules. All these produce the beautiful correspondence between the curve that you see and the data points. And there have been many such observations that I won't go through in any detail, but there are infrared bands, absorption bands, that imply the presence of biologically relevant molecules everywhere in our galaxy and in external galaxies as well. So these are wavelengths at which these nebulae, NGC 7027 is a planetary nebula, NGC 2023 is a star-forming region. They have absorptions at well-defined infrared wavelengths, and a mixture of 115 biologically derived biological molecules has the same wavelengths. These spectroscopic signatures of biomolecules show up in the most distant objects in the universe, signifying that biology is present not just in our galaxy alone, but almost as far as you can see, the most distant galaxies have biological molecules, which means that life is present almost to the edge of the observable universe. An ultraviolet absorption signature of dust, similar to biological aromatics, was recently discovered at a distance of nearly 8 billion light years. That little hump that you see on the left panel is an astronomical observation that was made recently of a distant galaxy, and the comparison on the right-hand side is with aromatic molecules from biology. So you see that this stuff is everywhere, not just in our galaxy. And even further, this little hump there and the signature there, I don't want to go into the details, technical details, but here is evidence that at 11 billion light years away, which is sort of very close within 3 billion or 2 billion light years of the formation of the galaxy, of the universe, of the Big Bang, you have organic molecules, complex organic molecules already present in vast quantity. And here again, this is also a very distant astronomical source showing the presence of biological molecules. So the universe was just 2 billion years old when the light from these galaxies display infrared bands that are unquestionably related to life. So seeing back into the cosmos, you see the extent of biology from present-day galaxies all the way almost to the formation of the first stars within the first million years or so of the history of the universe, filling a large fraction of the observable cosmos. The picture that I showed you, the Milky Way system in the first slide, is the Milky Way galaxy, our galaxy alone, just our own sort of home galaxy. But in addition to that, there are billions and billions of galaxies that fill the observable universe. Let's come back now from distant places back to the Earth. Life, I pointed out to you, first appears on the Earth in the oldest rocks during or shortly after a period of heavy bombardment by comets. The epoch that I told you was called the Hadean epoch. So this is a curve here that shows the impacts. It's a graph showing the rate of impacts, comet impacts onto the Earth, asteroid impacts, which is very high at the beginning here, and then goes down. And then there's a huge spike here, which is thought to be the moon-forming event. The moon was formed, we think, by a huge Mars-sized object hitting the Earth, splashing back material that orbited the Earth and condensed into the moon. And so that's the cataclysmic moon-forming event. And it was after this huge impact that you see the first evidence of life, strongly suggesting that comets carried this life and that panspermia is therefore valid. So let me next turn to comets, the invisible cores of comets from which these long, graceful tails emanate, have been the subject of scientific exploration and speculation until the dawn of the space age. It was not known until space science, until space observatories and satellites and so on probed these comets, what this tail and what the head of the comet was made of. After 1986, when there was the first space encounter with a comet, which is Halley's Comet, we know that comets are largely organic. And this is a model that was first proposed by Fred Hall and myself as early as 1974. It was a much denigrated model at the time because people thought that comets were just balls of inorganic ice. And when it was found that in 1986 that the comet Halley was more organic than ice, it was a big shock that the astronomers, conventional astronomers, had somehow to accommodate. These are pictures that show comets having organic material, liquid water interiors, and so on. I don't want to go into details, but you can see the picture of a comet as it goes around the sun and develops a long tail due to the heating of the surface layers. You get a huge tail of material that escapes from the comet. In 2007, the Stardust spacecraft visited a comet for the second time and actually photographed jets of water and organic material escaping from little cracks. These are amazing pictures showing jets of water coming out from a comet, showing that liquid water is present not very far below the surface of this comet. Direct evidence of water and life chemicals were therefore found from this comet Tempel 1 in 2011. So the theory then is that panspermia, life, originated early in the universe. It is carried still everywhere in the cosmos in the form of gigantic frozen planets and comets. If comets brought the first life to Earth 4 billion years ago, as I pointed out a little while ago, it's reasonable to say that this process could not have stopped. Comets are with us all the time. We see these comets approaching us from time to time. And so the process of bringing in living material to the Earth from comets must continue to the present day. So this is a picture of meteors, which are little fragments of comets, tiny fragments, millimeter, centimeter size fragments of comets coming in and burning up. That's why it glows and it appears as a incandescent blob there. This happens on regular meteor showers and also in sporadic meteor showers. In all, about 100 tons of cometary material falls through the stratosphere on a daily basis. Most but not all of it burns up on entry as meteors. The question that has to be asked now, if you're going to test the theory of panspermia and the theory that I discussed today, is can a biological component in comet material be discovered by present-day experiments? Can a continuing input of viral genes or bacterial genes be discovered, and could it even have an effect on the evolution of life? Occasionally, large pieces of an extinct comet falls to the Earth intact and can be studied in the laboratory to see if there are signs of life. A large carbonaceous meteorite, a meteorite that has a large carbon content, organic content, that disintegrated and fell into fragments near the town of Orgueil in France on the 14th of May, 1864, is pictured here. That's Orgueil, and that's a very famous meteorite. The Murchison meteorite fell in 1969 in Australia near the town of Murchison, and these structures, organic structures within the Murchison meteorite, were discovered in 1982 by the German paleontologist Hans D. Flug. His techniques of studying meteorites are perhaps the best that have ever been used to date. What he did was to take thin slices of the meteorite. So he had a meteorite, he sliced it into micrometer size, thick pieces of slices. He put these slices on a kind of membrane filter, on a till, and then he leached out all the minerals. And what was left on the till, on the membrane filter, was the organic material as it was, whatever it was as a virus or a bacterium, it was retained its original shape. So these structures here that you see on the left are what Flug found in the Murchison meteorite, and this is a corresponding bacterium called Pedomicrobium, a recent bacterium, a modern bacterium. The correspondences that he got were just uncanny and could not be dismissed as contaminants, which previous claims, there were claims for fossils and microfossils and meteorites in the 1960s, and they were somewhat suspect because the techniques were not as good as Flug's, and so the studies of Flug were the first really convincing argument for microfossils, fossilized microbes in a meteorite. This is, again, in the same meteorite, Murchison meteorite, fell in 1969, and he found a clump of material here organized exactly in the same way as an influenza virus. That the inset there is an electron micrograph of an influenza virus. In 2001, in a collaboration with the Indian Space Research Organization, a group of us in Cardiff and Sheffield, Cardiff group was led by myself and David Lloyd. In Sheffield, it was Milton Wainwright. And we attempted to collect some of the infalling cometary dust in the stratosphere. So they're not big meteorites. So what I showed you earlier was the Murchison meteorite was a huge lump of meteorite that fell in 1969. Now, in 2001, we decided to go up into the stratosphere and collect micrometeorites that are falling on a regular basis. I told you that something like 100 tons of this stuff falls through the Earth's atmosphere on a daily basis. A lot of it, most of it, gets burnt up as meteors, but not all. So some survive, and we wanted to collect the surviving pieces that reached a great height in the stratosphere before it got low enough. They got low enough to be mixed up with terrestrial environment. The collection involved sterilized what were called cryoprobes. Each of these tubes here was like one of these calogas tubes that you use for camping for lighting campfires and cooking in outdoors. They were stainless steel. They were evacuated. They were not filled with gas or anything. They were evacuated to very high vacuum levels of vacuum, and they were then flown in balloons to 41 kilometers above the city of Hyderabad, India, on the 20th of January 2001. The tubes were opened by remote control at the height of 41 kilometers, and so it sucked in all of the air in the stratosphere. A vast quantity of air was sucked in and frozen in these tubes. And this is what the tube looks like when it came down. The tube was analysis was done, I told you, in several UK universities and also in the USA and in India. And what we found in the air that was brought down in these tubes, the stratospheric air, was a large quantity of microbial dust, microbial aerosols that were microbial, unquestionably microbial. On the top here is a clump of spherical bacteria called cocci and a bacillus, and on the bottom are much smaller organic sort of particles that were identified as nanobacteria. There were quite a few of these on each of the in each of the cylinders, but more importantly, there was a vast amount of what were called viable but not culturable microorganisms. If you cannot culture a microorganism, you can still detect it. Microbiologists can detect the presence of these microbes by using certain dyes, and the use of these dyes showed clumps of fluorescent blobs like this that were identified as microorganisms. We argued that the height of 41 kilometers was too high for lifting microbes from the surface of the Earth. And the estimated daily input of microbes on this basis was something like 0.1 ton per day over the whole Earth. That's a huge amount in terms of microbiology. A similar balloon experiment was done in 2009 and yielded at least 3 new types of bacteria, one of which was named after Fred Hoyle, called Genibacter hoyle. It was a bacterium remotely related to a terrestrial bacterium, but sufficiently different to be called a new species. Okay, coming back to more recent experiments of the same type, Milton Wainwright in Sheffield University and I have, for many years, we've argued that it would be wise to repeat the Indian experiment at a time when we know that there is a meteor shower. The Indian experiment was done at a random moment in time, right? We know that meteor showers occur at regular intervals, and they are attributed to particular comets that are evaporating the debris from the surface of the comet and producing the meteor shower. So we talked about doing this, and very recently, only a few weeks ago, I think at the end of July, Milton and his colleagues and his students in Sheffield successfully sent up a balloon and collected material that was from the Geminis, from the Perseid shower, which peaked in late July to mid-August, and he caught the Perseids almost at their peak. The Perseids are from a comet called Swift-Tuttle. Milton Wainwright developed new apparatus. He developed a helium-filled balloon-borne sampling device that was launched into the stratosphere not far from where we are now, I think, in Chester, in northwest England, on 31st of July 2013. And this is the kind of device that he had, where he actually put electron microscope stubs on a like a CD tray that, you know, the old CD players have trays that can go in and out, and these were stuck on the tray, and this tray was opened by remote control, remote command at the height of the balloon when it reached its peak. And so the device included, as I said, the drawer mechanism that could be opened and closed any desired height using remote telemetry. Identical second drawer was flown that did not open at any time during the flight, because it's always important to have a control and to show that the control had no signal of any kind. The sample carried a video camera and so on. I don't want to go into details. I think this has all been very well publicized in the media in the last week, I'm told. The time that I was in Mexico, Milton was bombarded by media that carried the news of these discoveries. So let me just go through briefly what was found. These tubs that were exposed at the top of the flight, which essentially was lower than the Indian flight. The Indian flight went to 41 kilometers. This went only to 27 kilometers, but 27 kilometers is still high enough to be above the height at which aircraft flies and height at which particles are lofted from the surface of the Earth. So these tubs were brought back, parachuted back, and put under electron microscope. Nothing was found on the tubs in the control drawer that was not open to the stratosphere, and a large variety of organic material, organic particles were found in the drawer that was opened. So this is one clump of material that Milton's group found that had, these are undoubtedly biological filaments that straddle a whole clump of inorganic material. So there's no question that this is a living structure there, and with filaments that are organic. And here again, this is what they call the EDAX. He determines the elemental abundance in this little strip here and finds that that it's organic. This also, I think, was in the newspapers and so on. One of the objects that was found, bizarre organic material, organic structure, something like 20 micrometers, a huge structure, so large that it's impossible to have been lifted from the ground. And to me, the most important and most dramatic and compelling find of this experiment was this structure that is a frustule of a diatom. And you cannot deny it, because all these little signatures here, these little dots there, and the big pinholes there, and so on, they're extremely characteristic of a species of diatom called Nischia, and this was found dumped onto the surface of one of Milton's Wainwright's. But it did not come from there. It came from the top, and it also left a dent in the. I mean, you're laughing, but I think it's just absolutely bizarre. There's no.
There's been no response to this.
It's been published. It's been in the media, and the only thing that the Americans say is that this is too good to be true. It has to be a contaminant. It cannot be, and the general dismissal of any of this kind of stuff is to say that this is an extraordinary claim, an extraordinary. Yeah, Carl Sagan. But the extraordinary claim, I reckon, is to claim that life is confined to the Earth, right? And so I think it's all perverted. It's a perverted logic and a perverted science that is operating. So this is the Milton stuff, and so they could not have come from the skies, from the Earth. They are dented onto the thing. So I have no doubt at all. I just want to go through quickly these pictures of the atmosphere, and that's where the tropopause is. Nothing much can go above there, and this is where Milton's stuff is. This is where the Indian experiment was, way above the region where small particles can be lofted. Only violent volcanic eruptions can do it, and there was no such a volcanic eruption, either close to the Indian experiment in 2001 or close to the Wainwright experiment in 2013. Okay, finally, I want to just, before I deal with some philosophical and sociological matters, I want to talk a little bit about fireball events that took place in my home country, Sri Lanka, in December of 2012, leading to a meteorite fall two meteorite falls, one on the 28th of December 2012 and one on the 4th of January 2013. And these provide even more compelling evidence that meteorites are essentially bits of a comet, that these carry evidence of very complex microbial and microscopic plant life. So this is where the fireball sightings, this is a map of Sri Lanka, this is where the fireball sightings were. And on the right is and that's in inches here, right, is a fragment of a meteorite that fell on the 28th of December 2012. The location of the meteorite fall was in a rice paddy field. This is the area where the rocks were discovered. And an estimated 100 kilograms of meteorites were distributed over a 1 square kilometer area in this rice paddy field in central Sri Lanka. This is a guy who first discovered these rocks, the farmer Tikiribanda, and this is one of these meteorites. And so, fortunately, my wife and I happened to be in Sri Lanka in December, and we made contact with the people who were collecting these, and we were the first to bring back samples of this meteorite to the UK and to study them in the laboratory. They're very porous, very low density, unusual nature, unusual compared to most other meteorites, which sparked a ferocious controversy. And there were various statements made on the internet, and the internet has good things and bad things about it. And one of the things that was mentioned, to my amazement, was a meteorite collector, an American meteorite collector, saying that, this was a meteorite fall in Sri Lanka, and in Sri Lanka, in third world country, they don't know the difference between cow shit, a dried cow shit, and a meteorite. So it was regarded as being impossible because it was slightly different in appearance and structure from known meteorites. Most likely origin is that they were fragments of a porous outer crust of a comet, and as I said, untypical of the known carbonaceous meteorites. So it defines essentially a new class of meteorites, and there's no question about it. There's no question that this meteorite fell. There was a witnessed, well-evidenced fireball event. Unfortunately, there was no video recording of it, but there were witnesses and witnessed event, and so these were the images that came when we sectioned this in the laboratory. Amazing structures. Again, these are diatoms. There's no question that they're diatoms, and this is rice paddy field in the center of Sri Lanka, and these are marine diatoms. Okay. The sea is some 100 kilometers away from the paddy field, and these are all filamentous diatoms. So there were huge huge quantity of diatoms of different kinds. That's another diatoms locked in between the matrix of the meteorite. So you cannot say that it's just crept in after it fell. And that's more different types of really beautiful structures there that were part of so that's a close-up of it. Uncanny almost. And this is, I think, a very critical discovery. My student here discovered this structure here, which is carbonaceous. It's called a historic sphere or something, organism extinct for over 2 billion years inside this rock. So again, it cannot be a contaminant. And the most crucial test that was done was to look for the distribution of isotopes of different atoms. The oxygen isotope ratios, the oxygen comes in 3 stable isotopes, 16, 17, 18, and let's not go into the details of it, but there's a terrestrial fractionation line for these isotopes. All of the terrestrial rocks have this kind of this corresponds to terrestrial fractionation. This is the Polonnaru. Polonnaru is the place where the meteorite fell. That's where the Sri Lankan meteorite is. And this is where the carbonaceous chondrites, like the Murchison chondrite, fall. So they are distinctly non-terrestrial in terms of an isotope study, which is impeccable in its quality. It was done in University of Heidelberg, and the people who are the best in the world. But still, there is, I should say before I leave this slide, still there is a huge debate on the internet saying that this cannot be true, that these guys are not competent meteoritists, competent scientists, and so on. And all manner of character assassinations have been conducted against.
Does that actually mean that the elements that actually make that diatom are not actually from the Earth?
Yeah, exactly. If it was from the Earth, it would have had a certain ratio of oxygen 16 to 17 to 18, and it's different from. It's amazing, and there's not a shred of evidence. And on top of this, there's also the presence of high iridium. Iridium, don't know whether you know the Cretaceous Tertiary boundary where the dinosaur extinction event took place in 65 million years ago. There was a big argument whether the dinosaurs were made extinct by a comet impact or by some kind of ecological catastrophe. And the comet impact idea became almost the norm and the conventional wisdom after it was discovered that there was a high iridium content in the boundary layer where the impact took place. And now you have a meteorite here that has a huge iridium excess over any terrestrial material, and still the antagonism and the hostility continues. Okay, so meteorite evidence and adds to the wealth of other evidence that I just talked about briefly from astronomy, from geology, from biology, that all confirm that life is a truly cosmic phenomenon as we proposed way back in 1981. And this leads to wider and far-reaching implications. I want to just touch on this, a prediction that was made by Hoyle and myself in 1981. We said in our book called Evolution from Space, we wrote, if viruses are incident from space, then evolution must also be driven from space. How can this happen? Viruses do not always attack the cells they enter. Instead of taking over the genetic apparatus of the cell in order to replicate themselves, a viral particle may add itself placidly to one or other of the chromosomes. Viruses in our genes provide the potential for emergence of new life forms, potential for evolution, right? So we made this statement, we discussed it at great length in several books and so on in the 1980s. And now we find from the unraveling of the human genome, which was done in 2001, I think, was the first major unraveling of the human genome, we found that something like 50% of our genome, of the human genome, is made up of viral sequences. This was not known at the time when we wrote our 1981 book. And these viruses then were surely inserted into our ancestral line through devastating pandemics of disease. Our genes do indeed unequivocally carry the history of past pandemics. Human genome studies have shown that evolution of humans over 1 million years was marked by a succession of pandemics. And this is really quite beyond refute, beyond any dispute now. And these pandemics, each of these pandemics, were near close calls to total extinction. So you almost a total culling that took place of the human ancestral line at regular intervals, leading up from great apes and monkeys, anthropoids, to modern humans. So let me not go to this. This is the evolutionary tree that marks points at which these viruses major viral insertions were made. On this picture then, Darwinian evolution would have been accomplished over a large and interconnected volume of the cosmos, because I told you that one has to regard the whole galaxy as being a connected biosphere, right? You're exchanging material, exchanging genes, exchanging diatoms, exchanging viruses. Nothing of great innovation happened here on the Earth. That's a confession that people don't like to admit, I think. The Earth was just an assembly station, a mere assembly station for putting together the cosmic edifice of life. The tree of life, this famous tree of life with 3 branches, is, I would say, a trivial, and I stress trivial, reconstruction of a cosmically derived evolutionary scheme subject to natural selection. So, with all those evidences that I've discussed, I'm now going to just end my talk with a few questions that relate to sociology and to your conference, to exopolitics. So I ask, for how long could we deny the fact that life is everywhere in the universe and that bacteria and viruses from comets may still be raining down on us? The dinosaurs failed to recognize these facts, to their horror and to their eventual demise. Societal acceptance of evidence that life is all-pervasive in the cosmos is surely very long overdue. And I think if you can try to analyze this in terms of sociology and in terms of history, the resistance that has prevailed for too long is in fact a relic of the Copernican revolution, right? We had great difficulty in making the transition from an Earth-centered solar system to a sun-centered solar system. But the transformation took place. It was a long struggle, a long painful struggle, but the transformation took place. And the Copernican revolution, the bloody revolution, lasted for 150 years with the execution of Bruno, the imprisonment of Galileo, and so on. And long after, so this is where it started, 1450, it ended in 1750, a full 200 years, through Copernicus, to Galileo, to Kepler, to Newton. Let's hope that the next Copernican revolution doesn't take that long, but it may, I don't know how long it'll take, but that's the kind of situation that we face now. Long after the conclusion of this first Copernican revolution, scientists still opted to maintain that Earth was the center of life in the cosmos. So painfully gave up the position of the physical centrality of our place as the center of the universe, but we think that life is centered on the cosmos. Evidence I presented, I think, tonight can be combined with recent estimates based on a satellite that is picking up observations even now as we speak of Earth-like planets, exoplanets. And the number of Earth-like habitable planets in our galaxy alone has now been estimated to exceed 100 billion, and that's a misspelled there, 100 billion in our Milky Way alone. So there are 100 billion suns, we know there are 100 billion stars like the sun, and the current estimate is that there are 100 billion planets like the Earth, habitable planets. So the idea that life is confined to the Earth, or that the Earth is rare, must surely be abandoned. The universe must surely be teeming with life. If intelligence is the result of a process of convergent evolution, and I think there's every reason to believe that intelligence resulted as the end product of the piecing together of these bits and pieces that were flying around and happened to land on the Earth, if that was the case, then intelligent life must also be commonplace in the universe. The opposition to all these ideas has been largely cultural, but things are slowly beginning to change. Over the past decade, there has been a gradual realization that life must be a cosmic phenomenon. And many people who are antagonistic to this idea are beginning to voice opinions about what should be done to cope with the inevitable discovery that life exists outside the Earth. It's almost funny because they denied it for so long, and now they're sort of working on a contingency plan to deal with what happens when the admission is made that there is such life. Not long ago, I think a few months ago, in Davos, Switzerland, in a ski resort, in a beautiful ski resort, the world's business leaders, and politicians met to discuss global risks and challenges that would confront humanity in the next 10 years. And you would not believe it, that one of the top 5 global risks to be identified was the discovery of extraterrestrial life. Almost too funny to be true. This revelation, the revelation that there is extraterrestrial life, is reckoned would profoundly influence the entire future of humankind. The prevalence of life of any kind outside our cozy Earth raises issues that are connected not only with science, but with psychology, sociology, and religion as well. To some religious groups, the realization that the site of our creation was located outside this tiny planet may cause conflicts with theology. Earth-centered theologies and philosophies may need to be revised and reviewed. The discovery of intelligent life outside the Earth, if that does indeed happen, and I don't doubt that it might happen, poses the most serious problems of all, causing for fundamental revisions and readjustments of our perceptions of ourselves, of our politics. Our politics, religions, attitudes in general will all need to be revised and recast in the certain knowledge that we are not alone in the vastness of the cosmos. Let's hope that humility that ensues will make our world of the future a better place. Thank you.
Would you like to take any questions?
Certainly. Yeah, certainly.
Do you think something like bubonic plague might have come from space?
Undoubtedly. I think all of the major pandemics of history came from space. And I think also that history has more to do with the invasions from space than with the internal politics of kings and emperors and so on. If there was a plague, then the whole of the organization of society at that particular time would be in serious threat of disintegration, and that has happened many times. I think the plagues, probably all of the plagues, the plague of Athens, for instance, in the 4th century BC, the plague of Justinian, the bubonic plague, as you said, all of these certainly came from space. And the most recent plagues that have come from space, I believe, are the influenza pandemics. The influenza pandemic of 1918, 1919 is impossible to explain and understand unless at least a component of the virus came from space. For instance, it's been reported that the first outbreaks of the lethal second wave of the 1918-1919 pandemic occurred simultaneously on the same day in Boston and Bombay. And this was in 1918 when there was no air travel. So all of these facts that relate to the ancient epidemics and pandemics, I think, have to be reviewed. And once you say that life is outside the Earth and life started outside the Earth, and that the addition of microbial life and viral genes and bacteria continue to the present day, then I think the possibility, the certainty, near certainty of pandemics being brought from outside has to be taken seriously. I think that has to be one of the main consequences of the admission that there is extraterrestrial life. When in Davos, Switzerland, these guys have been asking, the politicians and the business people were asking for to enumerate risks that face humanity. I think one of the major risks would be to cope with a possible future pandemic. And if we accept that such pandemics can be caused from external infections, from extraterrestrial infections, then it will be prudent to monitor the stratosphere for incoming viruses. Okay, you could have something like a virus shield or a virus probe that looks at what's coming in and bring this stuff down before it causes havoc and causes devastation at the ground. Because it takes something like, for a viral-sized particle, it'll take maybe several years before it just falls through the skies, through the atmosphere to reach the ground. You could pick it up before it falls. You could send balloons. You could send various ways of collecting these materials before it falls. And if you spot an offending virus, then you can do something about it.
Can the ancient religious texts maybe tell us something about other kind of entities?
Yeah, I think so. I think the religious texts, the ancient texts, the Babylonian tablets are replete with the information that we need to understand and interpret. They haven't been done to this day to an extent that I think would reveal all these facts of the past. The Egyptian tablets have still to be fully understood, and so I think it's all there in the record if people think it important enough to unravel and to understand them. Yeah.
I mean, surely you'll be familiar with the argument posed by the likes of Richard Dawkins that, okay, sure, chance alone doesn't get the some building blocks into a microbial form because
Yes.
it would need many more times the age of the universe, like probability is just 10 to the 1,000. But it's a misconception to think that chance alone is all it takes, because there's natural selection.
No,
How do you retort?
I think they're just those are just semantics. If you try to put any of those arguments of Dawkins and our critics into in a numerate form, they do not work. I think
So even with the help of natural selection, Darwinian, building on positive mutations and sieving them through, you still think that it's not possible on Earth alone?
It's not possible. I think one has to argue that there may be a minimal genome that is needed to produce all the natural selection, evolution that leads to the whole spectrum of life. And that minimal genome is probably not much smaller than the Mycoplasma genitalium that I mentioned, which has 450 enzymes. Okay, so then that takes one part, 1 in 10 to the 10 to the 1,000, as I said. But let's say that you need 10 viruses with only 10 genes or something to start the whole process. Even that leads to a probability of 1 in 10 to the 100 or something. So nothing really works. I think these guys do not know their.
How would natural selection act just on the primordial soup?
I think it's hand waving. I think it's they believe so fervently that this is the way it has to happen, and that it happens easily. And if it happens that easily, my argument is that they should have shown it in the laboratory. From 1950, the Stanley Miller experiment has been repeated in dozens of other very sophisticated laboratories, mostly in the United States. And there's the various guys in California who have labs directed at this process, unraveling this mystery of the origin of life, and they haven't come anywhere near the arrangements of life. All that they have done, I think the cleverest guy in this area is Craig Venter, who has taken apart a bacterium and replaced its genome with another genome and so on. So, but you need the apparatus of the original bacterium to call it a living system. Yeah.
Well, thank you first for a great and fascinating and current talk. One question is,
So again,
What does that leave us with? How does this fit in the structure like your cloud, the cometary halo around our solar system? Is that just like a big frozen but living sea of?
yeah, it's a living sea of organisms. I think that the whole of the Oort cloud has a total mass that is maybe a few. Its total mass is not great. It's maybe a few times the mass of the Earth, but it's full of organics. And it's, I showed you that sequence from the Earth to the comets, to the galaxy, and so on. So that's the first collecting stage, sort of our nearest reservoir of living materials in the comets is in the Oort cloud. I mean, comets have been feared and revered by many ancient cultures, and I think that the tendency in modern science is to regard these guys as being primitive, and they don't really have any instinct or knowledge of things. But they probably had a deep knowledge or deep instinct that the comets were important for life and for the existence of life on the Earth. Which they are. I mean, if you believe the diatoms coming from in those meteorites, they're replete with life. Okay.